I'm making a class. What I'm going to do is demonstrate class rep and show how it uses stored compiler information. First of all, I'm going to fill in this record. Oops. Terminator. Okay, now class rep will get this it accesses the symbol table the compiler uses, and it will display. So it's kind of like a IDE debugger, but it's command line driven. Now it has the structures for pretty much everything. So now a similar feature is there's a metadata, which when you traverse the structure, you can access other data. This is a class declaration, and you can put an arbitrary metadata with a value, and then you can access it when you traverse the structure that the compiler built. So in this case, maybe you want a standard way to print fields, the string, or maybe you want default values. Now I guess in C++ you can already handle that, but in this this is not quite C++, but you can have default values or any kind of data. Up until the semicolon, it has name and then value pairs. Now one place it uses that is in forms. You can see here it if you do a form, then it can you can do the format string and tell the width and stuff. Now we're going to look at some features of the documents. Now the form we just looked at had a data widget. Now we're going to look at a text widget with a callback. Now we saw earlier how the LTFD and some other widgets are dynamic. Now every time it refreshes the screen, it calls a callback when it gets to this point, and the callback function supplies the text that it's displaying. Now a similar thing is called define string. Define load. Okay, let's say we have we're going to make a define string callback. So we Control L goes to the widget selection. We did a text widget, and the define string we want is test. So right here, whoops, why is it doing that? Okay, there it is. I don't know why it did that. Anyway, there's a text widget with the defined string, and the defined value is test. And oh, I know why. It's because it's not defined. That's why it's doing that. Now, if we do define test, okay, suddenly we have that word appear there. That's because it looked up the value in the compiler symbol table for test, and then it got that text. Now, define load, we can redefine it too. It's dynamic. That's how I show the age of the loose those and the line count and stuff with it's kind of like form letters. You can use define load is the same thing. Okay, so okay, now we're going to look at some compiler features. First of all, the compiler can be invoked from inside code with exe putS or exe printf, and it returns the value of the expression. So, for example, what this does is mgetS will prompt the user for some text, and it'll use malloc, so you can never have a buffer overflow. And then it invokes a compiler on what they typed, and then it'll print out that many asterisks, carriage turn line feed, and then it'll free it. So if we say 2 plus 3, oops, I didn't do 2 plus 3. We say 2 plus 3, we got 5 asterisks. Or if we say I64j equals 3, j times 2 plus 1, we got 7 asterisks. Or if we come up here, we say I64l equals 4, then if we run it, we say L plus 3. We got 7 asterisks. So anyway, there's a preprocessor directive that will jump to the shell to the command line and compile some statements, and then it can put text into the stream being compiled. So normally this is for static binaries, but we're doing it on a just-in-time. So it prints hello, it prompts for some code, and then it puts the code into the stream being compiled. And so if we say what is goodbye, and we got hello, goodbye, and we didn't have a carriage return line feed. Anyway, now it compiles statement by statement and executes. When it hits a function, it waits till it gets to the end, and then you invoke the function. So this is perfectly valid right here. You can define U8 is a character, and so we're defining an array of characters. It looks like it's variable length, but it evaluates it at the time it's compiled. It evaluates I at the time it's compiled. So that's how that works. Now, some tricks that lose those uses is it converts variables to constants, which makes them more efficient when the compiler runs. So it's really easy to convert a variable to a constant. Now, we're going to do a color change, color red. Now, the compiler is invoked even on is invoked on document commands. So if I say red +1 and switch back, we toggled to plain text. Now we go back to regular mode, and now it's purple. That's red +1. Or if we say I64, let's say LL equals brown. Then if we come up here and if we say LL, now it's brown. So the compiler's invoked all over the place. It doesn't have much overhead starting up, so it's used all over the place. Now, one thing I wanted to show is scoping. The compiler this is the Adam task. He's the father of all tasks. You don't type on his window. Tasks inherit the symbols of parents. So if we make a symbol, this will execute some code in Adam's by Adam. So we say Adam, let's say JK equals 6. We don't see anything. Now we have a variable that's system wide. Anyway, a regular variable is just like a local variable, local environment variable, but that's like an environment variable for Adam, and it's really elegant how startup works. All it does is it does like an autoexec.bat. It starts up. When it starts up, it starts executing this code, and these files load symbols and code into Adam's tables, and then at the end of startup it spawns some user windows, and those inherit all the symbols in Adam's tables. So it's really elegant. We're going to cover the compiling the kernel and installing onto a partition. Some of this is automated in the install wizard on the CD, but it won't mount all your drives. So you want to do an install boot on your own to add extra drives. You tell it the partition, it's partition D or the D drive, whatever you want to call it. Anyway, now this is called the configuration manager. What it does is it records your what you type to answer the prompts, and then you can automate it. I use a different technique. I'll show you in a minute. Anyway, we might as well record. It records it to. There's a what it's going to do is it's going to in my home directory there's a config directory, and it's got main is for OS main, master boot is for installing the master boot. These are different applications that have recorded configurations. Anyway, so current is the that's the current answer to all the prompts. Anyway, so we're recording configuration, and let's normally you do C as your base drive, but I use D for an obscure reason. I try to keep my two machines synchronized, and one has a C partition and one the partitions are a little different. So anyway, this is the D partition. That's the starting letter for the partition. So I have I think I have 3 partitions, so they're going to start at D and then go E and F, and it's a hard drive partition. We're going to probe, so we hit spacebar, and it happens to be number 2. That's for my system. Yours is different. Anyway, now we can either enter a 2 or we can enter 0. You have to put the 0x. We can either enter the base 0. I'm gonna do 2 just for now. Anyway, then we also want to make a RAM disk. You might want to. You got to come up with some use for all your RAM. I have 12 gig. Got nothing better to do than make RAM disks, and it's in blocks, not bytes. That's kind of blocks of 512 bytes. Anyway, T is what I use for the CD-ROM drive. You'll want to add your CD-ROM drive if you went through the normal install off the CD. It only puts your hard drive, so that's one reason you want to run this command. Anyway, the CD-ROM drive, a TAPI that's a CD-ROM. Anyway, so 3, and then we're all done. So we hit enter. Startup account. I made a directory called TAD. That's my start directory. That's my startup account. All the files in the accounts directory are the subdirectories of accounts are startup directories. So user is just a generic user. One will go through a tour. I kind of made bogus accounts on that. You'll see them. They're used for doing different options at booting. Anyway, so we want TAD. Here's what I did. Let me explain better. What I did is I made an account called install, and then when you log in as install, and if you log in as install, then in its startup files it runs the installation. So I did a little trick to give boot time options. Anyway, so we got TAD and disk cache size. We'll use whatever that is. I think that's, I don't know, 64 meg, something like that. It's all the files take up a total of less than 64 meg, so you don't, unless you're doing something else, you don't need a very big disk cache. Anyway, so there it just compiled everything. It compiled all the modules that have binaries. It compiled already, and now it wants to write to the boot partition. So I do 2. Now it's possible the probe won't be correct, and you have to enter the port numbers by hand. Anyway, if you have a system that's got some, I use the Intel chipset to get the port information. If yours is not an Intel chip, not the processor is not what I'm talking about, but some of the support chips. Right now, mine only it'll only probe for Intel chips, but you can use other chips if you enter in the ports. Anyway, this is a port number, an IO port number, this base 0. Let me do it by hand just to show you. So this is for the boot sector. So don't go with the default unless that's what it is. It probably is not what it is. And 0xb880. And mine, I have 2 hard drives in my system, and this is a slave hard drive. So what we just did is recompiled everything and put installed the Partition bootloader, not the master bootloader. Anyway, now that we have it saved once, we should be able to automate it. Install with the configuration manager. So like if you're working on the kernel and you want to recompile it, then you can say, let's use current as our current. We're selecting the current config. Oops, it didn't work. Well, theoretically, well, what I do is I have yeah. Oh well, I'll tell you what I do. I set up scripts that recompile everything with answers to the prompts. This where I enter my hard drives here, my RAM drives, and then I call install boot after putting some text into the keyboard buffer. Auto puts text into the keyboard buffer. It's like specifying standard in. Anyway, now when I do it, I just go right here, boom, and I compile everything. I also install master boot. I'm not going to do it, but install master boot. I guess I can do it. You enter the drives that you want prompt as options when it boots the computer. If you don't enter, it'll do all of them. Now you enter the base. Wow, it didn't give us a. This don't record. We have to enter that BC00. The probe didn't work on that. That's surprising. Anyway, okay, we just installed to the master boot record. Now, theoretically, we should be able to automate that. Let me try this config thing again. Let's use current config. Okay, there. You see it answered them. Anyway, so maybe it's the probes that present problems or doing the shortcuts. Anyway, oh well. So that's all you have to do to install everything. Now there's some things you have to know. There's a directory called boot00. It's got a file that it creates when you install the master boot record. It puts the old master boot record in this directory, and it needs that to chain load whatever was there before you installed. Lose those, and don't lose this file. Like, copy it onto a CD so you have a copy. Because, like, if I format my D partition, I might lose that file, and then I'd be in trouble. I think it puts it on the recovery disk. I'm not sure. Anyway, so that's all there is. Let's go see why it. The reason it prompts when you compile is because it has some .exe directives. Here's where it asks for startup account. So when it compiles the kernel, it hits this little block here of code while it's compiling, and basically this shells to the command line and gives the option of streaming code into this spot. So what it does here is it when it finishes those prompts, it actually adds in some code like this right into the stream of code. So anyway, so that's how that works. Now the configuration manager you can use for your own modules to manage stuff. There's a if you're curious where the install boot is, it's in the optional directory boot, and let's just go to now the source drive is the destination drive might be different if you're making a CD-ROM bootable image. Anyway, I was going to show, here's where it calls a configuration manager. You can make your own configuration if you want for your own modules, but you don't normally have to do that. You probably won't make static modules. But, well, that's it. Let's take a quick peek at, I made some documentation on installation, booting. So the master boot record is block 0 on your hard drive. It loads in a loader that does the menu. It's got a little more. That's stored on your lose those partition, as well as that's where the remember where it was the old master boot. Well, there's also the loader on that partition. So if your D partition got destroyed, your master boot record or formatted, then your master boot record wouldn't know where part 2 was. It doesn't use the I think most people use some blocks 0 through 31. Anyway, it doesn't use that. You don't need to worry about it. Anyway, then the master boot record loads the partition boot block, and then that starts up everything. Anyway, that's the sequence during boot. Anyway, I recommend using grub as your that's the Linux bootloader, so install master boot. That command affects these two. Install boot affects this one right here. So you need that even if you're using grub. You still run install boot. Okay, well, good luck. This is Lose Those, a 64-bit operating system for the IBM PC that's free and open source. It's designed for recreational programming. I wrote this over the past 7 years full time, and I did a compiler, an assembler, an editor, a graphics library, and it's all 64-bit, and it's all seamlessly integrated together. Anyway, it's predominantly command line driven, but you have a menu that personal menu that you can put macros on. It's a document, and if you like icons, you can do icons too. They're just macros that have pictures. We're going to click on this flight simulator. This is an 8-core flight simulator. Up here at the top, you can see the CPU loads. It's 640 by 480 by 16 color resolution because it's hard doing full screen 60 frame graphics without acceleration. Anyway, the command line feeds into a C compiler. Actually, it's C plus or a slight flavor of C. Anyway, it compiles incrementally. So we're going to do, actually the native type system is use0 for void. You can use the standard types if you want. I64, it's a 64-bit integer signed. Normally you don't enter functions at the command line, you put them in a file. There's no difference between the command line and source code. Anyway, there's a slight difference, but we won't get into that. Now I entered a call to that function. It's outside, it's at the global scope outside the function, and that gets executed immediately. Anyway, we just counted to 10. Now since it feeds into a C compiler, the way you invoke a file or call a file is to do an include. We need a semicolon because it doesn't know that it's done. There we got hello world. That was a file, hello, that was just printf. Now we're going to do another one. This is just an alternative. This is not quite the standard C out from C++. It's a slight it's a special case in Lose Those that's just handy. I'm just showing it because in case you see it, you'll wonder what it is. Anyway, it uses commas instead of shift operators, and we're going to do a number in that. Anyway, you can right click on these links are active at the command line, and so we just got hello world and then 1 2 3 4. We're going to do another example. We're going to do a directory. This is C, as you can see. Anyway, files ending in Z are compressed and uncompressed on the fly. So the next one we're going to look at is actually it has default parameters from C++, and if you have no parameters, you don't need the parentheses. Kind of like Pascal. Looks like Pascal, doesn't it? Anyway, we're going to look at this example. This turns on the compiler trace, which will unassemble the code as it's compiled. And just to make it interesting, we broke it up into a cout for hello, a put s, and then carriage return line feed. This is just a handy function. It doesn't have parameters, so there's no parentheses. Anyway, and then this is going to invoke that function and then invoke that function. See it, and then turn the compiler trace off. You can see it's exactly what we've been doing. So carriage return is the same as right click. Now this is 64-bit disassembly. It has source debugging, so you can jump to the code with these links. 64-bit assembly. Take note of this call. That's the invocation. That's where we did the invocation outside the function. Then there's another one, and then there's a call to turn C trace off. Anyway, you don't have to know assembly, but if you're interested in recreational programming, there's a good chance you're interested in assembly. So now we're going to do hello world from assembly. The standard is db for defined byte, but the native type system is U8 is a unsigned 8-bit, and it's for characters you do unsigned instead of signed, because signed is kind of stupid, isn't it? Anyway, so it's carriage return line feed at the end, and it's got a 0 terminator. : is a exported symbol. We have to preserve RSI, and then we load RSI with the message and call put string. This ampersand will import. Right now we're operating in just-in-time mode. When you compile binaries, it's a little different. Anyway, then we have a call to that exported symbol, hello world. So we're going to run that. We got hello world. Now, if you want, you can hit F5 when you're in the editor to run a task. It spawns a task, and to run a program, it spawns a task and runs it. So we just did that. Now we're going to include, we have a factorial function. We're going to include that, and now we're going to go on our menu. I hit the Windows key to get to my menu, and we're going to make a macro. Now up at the top is these red ones are links, these blue ones are macros. That you can have trees as well. The document structure supports a lot of widgets. So links, trees, colors, you can change colors, margins, and macros, and even the forms and dialog boxes use the same document structure. Anyway, so we're gonna click on macro, and we're gonna say factorial, then the expression. We're gonna create a global variable I for I equals 0, I less than 22, I plus plus. See outline I space factorial I, and then we need a carriage return at the end. So now we can click on this, and we get the factorials up to 22. You can see it's 64-bit. Anyway, now we're going to look at I want to show a couple miscellaneous features. There's a zoom that's system-wide that will zoom on the cursor. So you Control-Alt-Z will zoom in on the cursor. Control-Alt-Shift-C will zoom out. There's also drag that control and then left drag will scroll. You can have scroll bars too. Anyway, it's got scroll bars, but it's the nice thing about these system-wide features is you don't have to add them to your applications. So if you want a scroll feature, this is done at the graphics library function level. Anyway, now we're going to take a tour of the directory, the standard directory structure for lose those. It's this is my personal version. I have a few more lines. It's 120,000 lines of code. There's an accounts directory. There's Adam. Adam's the father of all tasks. He's the first task, and he starts up running a script like AutoExec, and he compiles a bunch of code into his heap and symbol table, and then other tasks can access them if they're children of Adam. Anyway, so all this code gets compiled during boot, and then there's optional packages which are also compiled during boot, and they're placed in memory. It only takes 2 seconds to compile 40,000 lines. grep is an optional package. They don't, when you enter a command, it runs from memory. It doesn't operate like Linux or Unix, where it goes, or DOS, and executes a file. It doesn't do that. There's no path either. Anyway, so optional packages, Atom, accounts. Then there's applications, and there's my compiler, and it's a compiler, assembler, unassembler. Then there's the kernel, although everything runs in kernel mode, so it's nothing special. The user programs run in ring 0 kernel mode. Anyway, this is the compiler. OS main and OS main 2 are compiled ahead of time. Everything else is just in time. OS main 2 is just sprintf. Anyway, if you want to, well, let's look at a quick. There's tons and tons of demos. We're going to look at, just to show an example, I said everything is seamlessly integrated. This is source code here with graphics in it and links and stuff, and the compiler understands it. Anyway, so now let's recompile everything that's done ahead of time. There's a feature called WordStat, which will do auto-completes, and it'll jump to source code. So we can do Control-Shift F1, jump to the source code. So all the documentation is pretty much right by the code. Anyway, this is gonna compile everything that's compiled ahead of time, and it's gonna tell the boot sector where the block number for the kernel is. This configuration manager is flaky, but let's hope it works. We're going to use the current configuration for the kernel. Okay, it worked. What I do actually is I have a key on my menu that compiles everything. And if you want to see the code for that, you can go to anyway, it's in, actually, I have my personal files as an example on the distribution. I load up my answers into the keyboard buffer so that it does standard in. That's what this auto function does. Anyway, here's the wallpaper underneath here, and it's got this is 8 cores, and it's got the memory. I have a 12 gig machine, and actually the lowest 2 gig is for the code heap. It separates code and data so that it can use 32-bit branches, which are the fastest. They're faster than system calls. Anyway, this tells where the tasks are, where the task codes are sitting, and tells how many lines. 40,000 lines is compiled during boot, and 40,000 ahead of time. And let's just do one last demo here. We're going to make a byte pointer A. We're going to malloc 8 gig. and you can see it just dropped that 2 in the leading 2, so that's 8 gig. It has to be it rounds up to a power of 2, and on 12 gig machine, the biggest I can allocate is 8 gig. Anyway, we know we're going to set that to 0 just to show that it works. Everybody uses the same address space. It never messes with maps or page tables. Set it to 0, and then free. It's 64-bit. There's that issue with the bottom 2 gig for code, which is it is 64-bit, but it does have that issue. Anyway, now the memory's back up to 11 gig free. Anyway, now why don't you send me an email if you want the full version. The full version has a dictionary. It's free. Anyway, I'd really like some emails because I don't get any feedback. And anyway, watch the other videos on the site and have fun.
Okay, press F1 to get to your help. Then go to key map. Control-Alt are system keys. Those are system-wide, not intercepted by the editor. Alt keys are user-defined. Alt-M and Alt-M is max. Alt-V is a tile vertically. Some of those are handy. You can do your own keyboard plugins for those. The control keys are mostly editor IDE. We're going to look at just a plain old F2 or F4. F4 is this is the keyboard handler. It calls pop-up pick file, pop-up pictor. Those are file choosers. Control D is the file manager, and it turns out that if you let's do edit, Alt M for Max, and we're going to hit F4. Okay, you got that F4? That does the file manager, which is the chooser, and then we hit escape to exit when we're on top, and there it is. There's the file name, so you don't have to type file names if you do that. You can do file directories with Shift F4. Anyway, so it turns out that you change the first letter of the command a lot of times. The drive number, you change it to colon for the boot drive. Anyway, now if you want to search for a string in a file, then you can say find FF. This is find string, and this gets crazy, but these have a colon, and then there's a colon, and let's search for how about alt, or yeah, let's search for alt. Alt is the string. Okay, now we're on top of alt. It found alt. Now if we say F:2, it found the second occurrence of alt. Okay, so what we just hit upon was the link types. The editor actually takes a link. You can enter a file or a link, a file name, an anchor in a file, a string, a second occurrence of a string, a file line number, or you can do plain files. The Sparrow OS uses $ commands. $ are special for documents, and if you want to use plain non-Sparrow, you can do that. You can search for a book in the Bible. You can search for a definition of a word in the dictionary. There's a help index. There's a you can enter an address. It'll jump to source code, or you can enter a symbol for a man table entry. Anyway, if you don't have a you can enter a file name, or you can enter a link. So this is just a file name, and anyway, now it remembers the position of the cursor. It puts a ASCII 5 for the position of the cursor. Watch this. So let's put the cursor down here. I'll hit escape for exit and save. Now if I do this again, it comes up in where I left off. Anyway, the FF, this is find file. Let's say star slash star dot txt star semicolon star dot dat star. Okay, this is kind of crazy, but it's almost like there's the directory and then a list of file types. The directory you put first, and that's the base directory, and then you put the file types. That didn't work. One thing, by the way, control B brings up the border. If you ever enter a quote, notice the quote down here. We have an open quote, so we just got rid of that. Anyway, going back up here, star find file. Invalid file name. Okay, well, I don't know. Anyway, so it did .dat and .txt. You have to, if we say sparrow os slash accts slash star. Okay, anyway, so the FF takes a file mask, which is one of those directory and then file type things, and then it also takes a FU flag. The FU flags are FUF. These are recursive, hold labels, question, just source, just directories. Anyway, these are FUF flags. A lot of commands take the FUF flags. We can do find, which is grep FUF, and then -I is don't ignore case. So these are all the FUF flags. This is a grep. F is grep. It's my own personal version. It's customized. It's a wrapper function. Anyway, so if you want, there's some handy, let's see. Now if you just do directory like this, you get a ton, because it's all anything with, now if you say F directory -I plus L, that's whole labels, that's whole words. Now it's only ones with actual. You can do F front label or back label. So if we say -I plus label front, it won't let you have anything on the front. So when you do that, it doesn't, see how it starts with dir, but it doesn't. Anyway, so let's go to this web directory. I just want to show off a couple things here. Here's a bitmap. We can type a bitmap file. I just typed it. Now we can, if we go to home, we can type my personal menu to the command line. Now on the command line we have graphics and anyway, now let's do a partition rep. We have ATA is hard disk, ATA API is CD-ROM, and then we have some RAM drives for doing custom things. For doing images of CD, sometimes you want to use a RAM drive for image of an ISO or something. Anyway, I have a CD-ROM drive on T. Now, removable disk, you need to know. Okay, you can say drv drive T. Any of these commands that take a drive letter, you put in single quotes because it's C. Change disk. This is a removable disk, so that doesn't automatically detect removable media. So you have to change disk. If you change the disk, you have to enter this command. Otherwise, the cache is invalid and stuff. Anyway, we're going to do. This is how you install. I'm gonna copy my E drive to my F drive. How about, yeah, F drive. Okay, so I keep my E drive is a backup, and then my F drive is for transferring in and out. I keep an exact snapshot, so I can reinstall in like 5 minutes. And I make ISO files that you want to learn how to make an ISO file. Look at the account examples. Anyway, then we're going to there's two binary files that are compiled ahead of time, the compiler and OS main, and we're going to do a make all. There's only 2 files that get made. Anyway. So the make all is done with install boot, because we have to tell the new location of the kernel, because the bootloader uses an absolute block address. Okay, so we just copied everything from the E drive onto the F drive, so we have an image. We didn't format first, though. We probably should have. Anyway, Bible, everything. Now, when this gets done, we're going to install boot. There's an uncompressed utility called TSZ that'll run in Windows. The files ending in Z are compressed, and you can uncompress them in Windows if you want, or you can do a move in Sparrow and it'll uncompress them. Anyway, install boot, F, then we enter base drive D. It'll find D, E, and F, so we do probe. You either enter the ports, or if it has a number, you can enter a 1 for the number. It knows that's not a port. Oh, I didn't do my CD-ROM. Anyway, TS/TAD is my account. Disk cache size, use default. Protect low will check for a null pointer dereference. These are options for the kernel. So we just recompiled the kernel and OS main and the compiler. There's line count rep. Okay, so just as a tour, there's the compiler is 21,000 lines, and OS main, which is the kernel, is 25,000 lines. So there's about 50,000 lines that are compiled ahead of time. There's a binary file for the compiler and a binary file for the OS main, and everything in Atom gets compiled during boot, and then the accounts code gets compiled during boot. Then you have applications that are compiled just in time when you run them, or miscellaneous and demos. I want to make a comment about home fixes the drive as well. Anyway, I want to talk about there's different link types in Sparrow. You can enter there's file, anchor, find a string in a file, a line number in a file. That's pretty common. A man page, which looks up a symbol. and then there's plain text. Sparrow documents have $ commands, and you might want to edit a plain without the $ command special. Anyway, it'll look in the Bible, it'll look for a definition of a dictionary word. There's a help index or an address. Anyway, if we say ed, if we say ed, then if we do F4 for picking a file, then we go and we change the first letter to the boot drive. So doc pop-up. Let's look for, if we say find file, : that'll find a string in the file, doc. There we found the first occurrence of doc. Let's do the third occurrence of doc. There's a third occurrence of doc. Let's do file line. Let's do line number 200. I'm going to discuss technical details. When it boots, it starts, it loads the OS main.bin. The bootloader loads OS main.bin. This is the project file for OS main.bin. The first bit of code is right here, include OS start. So it's a flat binary, and it starts at OS start. That starts in 16-bit mode. The bootloader hands it off in real mode, and it calls some BIOS routines to change to VGA graphics mode, 640 by 480, and it calls some BIOS calls for information on memory and number of buses and stuff. Anyway, OS start calls OS end, and there's run levels, which are it's not there. It sets bits telling when it achieves certain achievements. Anyway, the last thing, the first task is called Adam. He's on the bootstrap processor. That's what they call core 0. I like core 0 is more clear. Anyway, and when he's done, it starts off, OS main is loaded in to the bottom 640K. Then it changes to 64-bit mode, and it loads in the compiler. And finally, after it loads the compiler, it calls, this is like the autoexec.bat file. It calls Adam1. Okay, now each task has a symbol table. You can kind of think of it like environment variables, except it can have functions, and it can have variables, and it can have classes and stuff. And Adam is the first task, and every task has a symbol table. It's a hash table. Anyway, Adam, when he starts compiling this code, these are the headers. These are the main headers for everything. Pretty much everything goes in one header file. Well, there's the classes and classes and defines are in Adam 1A. The internal function headers. These are to bind the assembly routines to C++. You use extern to bind assembly label to C++, and it's a flavor of C. It's more than C, less than C++. Anyway, the compiler has some built-in functions. It doesn't have inline functions, but it has some internal functions. I can show you how to add one. When I upgrade, sometimes you have to start with the new compiler. in order to compile code. Anyway, because I make syntax changes. So these are the, this is the third header file. These are the regular C externs. This Atom1 is compiled and it loads all those symbols into its table. Now, line count rep. Remember we said it starts with OS main. OS main is, this is a line count rep. OS main is 25,000 lines. The compiler is a binary and ahead of time, compiled ahead of time. It's 21,000 lines. So about 50,000 lines is compiled ahead of time. The rest of it, since Atom is the first task, he goes about loading in all those headers, and then he actually loads in, he compiles a bunch of code just in time. The reason I do it just in time instead of ahead of time is because I want to. You don't need object files, you don't need executable files, and I just like it. Anyway, so I try to do as much ahead of time or just in time as possible. And it starts in OS main when it boots. That's where this Atom1 file is, and then it hands off to Atom2, which is the next stage. That's the code that's compiled during boot. So there's about 40,000 lines compiled during boot. Atom2 is the start. It just includes all these. Some of them are directories. This is the graphics library. I do all the graphics from scratch. Anyway, bitmap has, this is the plot pixel. There's plot, I do plot triangle, plot everything. Anyway, GR screen has, first of all, there's a special task called the window manager task, and it updates the screen 60 times a second. It redraws everything. Invalidate rectangle doesn't help if you have a full screen video game. Therefore, I don't do invalidate rectangle. I don't care about power. This burns electricity. I like desktops. Anyway, so the window manager task calls. Okay, there's a text layer, there's a persistent layer, and there's a graphics layer. And this is all done by hand. Anyway, update Windows. This routine is called 60 times a second, and it goes through all the tasks on core 0, and calls all tasks. All terminal tasks have a document for their command line, and this goes through the update task docs. It goes through the document for the command line. It also has a you know how Windows has a mainframe and a client area. Well, in Sparrow OS you have an auxiliary, which is the border that there's the border text is done with the document, and then the main client area is done with a different document. You can have one window per task, and there's no difference between process, thread, and task. Everything is a task, and every task can have one window if it's on core 0, and every task has a symbol table. Every task has a heap, and child task inherit symbols from parents. So since all tasks are children of Adam, so they get all those symbols that were loaded in at boot. Anyway, so it calls update. That writes to there's a text layer. It's not B8000. It's actually 32 bits instead of. It's got extra attributes for superscript, subscript. It's actually done with extra attributes. Anyway, so it calls, updates the document. Then task can have a draw for drawing to a device context, a callback. Now I use this task validate because normally you wouldn't need this in a regular operating system, but this is for you to poke around with. When I had a Commodore 64, I used to modify the ROM, the basic RAM variables and stuff. This is for users to poke around with. So since you're going to be messing around with the task, I try to make it a little more robust by seeing if it gets a bad task and then bailing out. So task validate is in a lot of places. It checks task validate, checks if it's in the, it goes in the lowest 2 gig addresses. It checks to see if it's tasks. The current task is pointed to by the FS segment. You have to, in 64-bit mode, you have to set it with the right model specific. Anyway, so the lowest 2 gig is special in TempleOS because, well, that's the lowest 2 gig is for code. I use only call instructions, and calls have, anyway, it also puts task records in the lowest 2 gig incidentally. Anyway, it has a signature. It checks to see if it's in the queue and stuff. Oh, then the other thing is controls, scroll bars, and you can make controls. Those have tasks can have controls. Anyway, let me go. Memory. So the bootloader relocates itself and loads in OS main at 7C up to 3F or 3C. I have a lot of extra room in case it grows in the future. Then the page tables are at whatever that is, 1 meg. Up to I use in 64-bit mode you have 2 meg pages. I map everything identity mapped with 2 meg pages except the lowest 2 meg, which I map with 4K because it has to set the VGA is right through. Anyway, so up to the code heap is the lowest 2 gig. That's so that it can use the call relative 32 instruction everywhere. TempleOS is ring 0 only, so it never leaves ring 0 mode. So it has no protections, but it's like DOS or like a Commodore 64. Those didn't have protections. It's intentional that way because when I had a 64, I used to play around with disk blocks and play around with just for fun. You can, you know how video games entertain for 30 hours? Well, if you poke around for 30 hours, watch this document dump. FS points to the current What is... Oh, FS. FS points to the current task record. You see how it's updating live? There's live widgets. Okay, so 64-bit mode doesn't really have segmentation, but it does support FS and GS. FS is kept pointing to the current task record, task structure, and the first address in the task structure is a self-addressed pointer. That we'll get into that in a second. Anyway, so a task record has stuff like there's one window per task, and these are the window dimensions and position. The registers, when the scheduler swaps it, tells the GS segment points to the current CPU structure, and this is the task CPU. It has it has the callbacks for drawing, and it has anyway, this, you want to get familiar with it. I add user data that's for you to play around with. It's not really a workable solution. If you want to add extra data, you have to create a frame in the symbol table. Anyway, that's the proper way to do it, unless you're me and you can modify the structure. So if we say class rep D, this is a all the information the compiler has about classes and stuff is still available. So the class name comes first. We want C task, and then you give you do your debugging at the command line. So that this will dump a structure dynamically. So it knows all the compiler information about this class, and it shows all the members, and you can go deeper. The FS segment register is kept pointing to. Let's look at. The first one is self-addressed. See, well, you can't really, you wouldn't know the difference. Anyway, so the FS segment register is kept pointing to the current task. The GS is kept pointing to the current CPU structure. If you want to see what a CPU structure looks like, it has a number, that's the number of the CPU, and it has the idle. You need that when you're scheduling. You monitor how much load it has. That's the complement of the CPU load. That's pretty much. It has a interrupt descriptor table, task register. It has a Seth task. Seth is the child of Adam, and there's one special task on each CPU that's the Seth task, and it needs an idle task too. Anyway, where was I? The FS and GS have to be changed with right model specific register, and then it gets really tricky. Let's look at how we want to get the FSRIP. What it does is it this 32-bit displacements are RIP relative, which the addressing mode is inconvenient. So what you have to do is you have to XOR to get a 0, and then load an offset off of 0 instead of just an offset. And ideally, if this were 32-bit mode, you would do it like this. but in our case you have to do it with this XOR 0. And there are times when you have to get the self-addressed, the FS is the first value is the self-addressed value. Anyway, so so the class rep D, the document D FS, this shows you can modify this live. You can also modify class rep D. You can put a size. So the window coordinates are somewhere in here, and we can modify. These are live widgets. To show that it's live, let's go back to whoops. Okay, so this document has a widget. When it was created with a Control L will create a widget. Create a widget. If you do text, and you can say nothing, and define string. If we say my define, we just created a text that's my define. Now if we say my define help, then if we come in here it says help. These are string indirection, and it works. Lose those is for dynamic documents, not printing. I decided, unlike everybody else, I'm not doing a stream. I'm not doing, there's not a standard in, not a standard out. These are dynamic structures. This is not a general purpose operating system. Anyway, so where was I? So the bottom 2 gig is called the code heap. So when it puts global variables, and it puts code in the code heap, it keeps track of which task owns it so that it frees it. That's because, do you understand if I say ASM here, call, let's say DU8 testing, comma 0. Actually, I shouldn't have. We have code trace on. That's why. Here are 2 bad labels. Push RSI, move RSI, comma here. Call address, put string. That's an import. Look at the example code to learn these things. I don't have to. I should do ES. Okay, so I just made some code. Let's unassemble. Unassemble works with for functions. You put an ampersand. If it's a assembly, if it's a C function, you put an ampersand in front. Otherwise, you put just the assembly symbol. And for assembly, you can only have the symbol defined once. For C symbols, you can redefine them, and it overshadows. So let's see, we want unassemble here too. So when we unassembled here too, we have code trace still on. Code trace off. Now unassemble here too. Okay, so here's the push. Look at this. It loaded a 32-bit value. That's because it's in a code heap. And then it did a call. This is a 32-bit. This is a 32-bit call because it's in a code heap. If I didn't have a code heap, I would have to work a lot harder. I would have to use more instructions, and then it does a pop. There's not a most operating systems have kernel in the upper memory. I don't have that. I just put all code mixed up in the lowest. So it just printed testing right there. So I put all code in the lowest 2 gig, but I can allocate big chunks. Actually, memory can get fragmented because I don't use. I always identity map. Now I give lectures on if you want to play with page tables, I set it up. If you want to play with ring 3, I set it up. If you want to play with PCI interrupts, I give lectures on that in screen memory and timing instructions and some tricks. So you probably want to look at those. It's identity mapped, so all tasks on all cores have access to all memory at all times. There's some device memory in a gap. The lowest 2 gig is code heap, then there's some data, then there's a gap for 32-bit devices. I don't really do any PCI devices. Then it can go up to I think 64 gig or something, or I forgot, 128 gig. What did I say? These are dynamic. You can change the limit. Anyway, I want to show one more thing. What was I going to show? Okay, so Control Alt Escape creates a new task. Alt V makes it vertically tile. Let's get rid of one. Shift Escape. Alt V. Okay, so now we have 2 tasks. Now let's say I64. Let's do I. There is no I symbol. So if I say I64I equals 1, 2, 3, I just made a variable I. Okay, now it's 1, 2, 3. If I come over here and say I, that doesn't exist. Now, what about J? That doesn't exist. Now, if I say Adam, this Adam sits in a server loop, and he will compile code for you. Adam J. Now, since everybody inherits Adam's symbols, if Adam defines a global variable J, suddenly J equals 567. Suddenly, everybody has J available because everybody inherits his symbols. So he has J now. You can do a map of all symbols, alphabetical order. I keep everything. When I had a Commodore 64, that book told what everything did, and that's what my goal is. Okay, so if I come over here and type FS to get the task record, you see this number matches the number up there. If I say X crosstalk 0x 7F D15028, I enter that's like the process ID. It's actually we just use the word task, not process. Anyway, if I do directory carriage return, then it sent that to this guy's input buffer. Now, if we we can do this with Atom as well. Atom sits in a server loop. We don't need a carriage return with Atom. Anyway, so he sits waiting. Atom is like Atom's heap is like kernel memory. It never gets freed. So if you want something never to get freed, or you want code that's never going to get freed, then Atom include, and he'll include a file. So we go to demo graphics and fish, and we Atom include. Okay, so the wallpaper is Atom included. Now if we say task rep, this is a I don't use this very often. I just use a wallpaper normally. This shows a hierarchy of the tasks. Atom is the first task created, and he has children on he has this is the terminal task. This is the frame grabber that's making this video. Then the window manager updates the screen 60 times a second and does a couple other things. Then there's a special server task for on each core. It's kind of like the Atom for that core. Anyway, if you click on these, it'll kill the task. We don't want to do that. Atom never dies. His memory never gets freed. Anyway, so the window manager calls this routine 60 times a second to update the screen. It has a cache. Well, okay, first it has an array for the text. It writes the background, then it does the foreground. The foreground can be shifted according to superscript and subscript and marquee. You see up there's a marquee. That's done with shifting it off the axis, or off the grid. It calls that update window we talked about earlier. So the buffer is 8-bit together, but when it does the mouse cursor, and then it converts it to 4-bit. And it only does what's changed. It only writes what's changed to the VGA memory. That speeds it up a lot because the VGA memory is slow. But in a worst case, it doesn't speed it up. So we're going to talk about the scheduler. If we go to OS main, the scheduler goes in a loop. Round robin, and it doesn't save segments, it just saves registers and breakpoints. Breakpoints get removed when breakpoints are associated with a task. I almost never use breakpoints. They're with the window manager doing callbacks, the breakpoints are all screwed up. Anyway, so I do printf debugging. So it's round robin. And when it gets to a task, it checks if it's suspended or if it's waiting for a jiffy, wait jiffy. If it's not, it skips it, goes to the next one. It has some flags for hotkeys like Control-Alt-X kills the focus task, Control-Alt-Delete reboots, Control-Alt-Tab switches to the next. Now the multi-core task stays in a loop, and it gets a timer interrupt 60 times a second. It stays halted. You can wake it with there's a software interrupt that'll wake up a core, non-maskable. Anyway, you either do a job or you do a spawn. A job is a one-time thing. A spawn is a task. So the Seth task either does the job that you tell it, or it spawns a task and then it continues. Multi explicitly you tell what core you want doing a job. Anyway, the timer interrupt lets it figure out how much idle time it has. That's why it gets a timer interrupt. So we're going to talk about the file system. If it ends in .z, it's stored compressed. If we copy or move it to a name without z, then it's uncompressed. All there is to it. So this file is uncompressed. Now let's do a dump cluster, or let's do a directory star true. This cluster compressed. If you use the native file system, it keeps track of the uncompressed size. The FAT32 is all you need because you can grow files. With the native file system, you can't grow a file. Anyway, so this tells the cluster. It's dump cluster. You give the cluster and then a bool for if you want to write. So 0x, there's the cluster, and we do want to write. So here's the cluster. So in the file, we're going to change this to D, let's say FFFF, and it told us to press escape, so we press escape. Now we do a directory, and now this file starts with DFFFF. So we wrote to the cluster directly. Anyway, there's checksums when you use the native file system, and it's 64-bit, but it won't let you grow files. That's because there was a patent on the FAT. Now we're going to go look at, remember I talked about making a named name frame pointer. Basically, this is the entry in the symbol table, the task symbol table, that has a value. When we want to make a noise like an explosion or something, we make a record that has the high frequency, or the min frequency, max frequency, duration, and then we spawn a task that's in charge of that, and we have to pass it that record, and it sticks it in its symbol table, and then when this task dies, it knows that it can free that. Anyway, so that keeps it from leaking memory. Anyway, so the compiler has a opcode table. Now, the opcodes are, there's no push AD. You can't push all registers. That only works in 32-bit mode. All stack operations are 64-bit in 64-bit mode. That means if you push a 32-bit register, it pushes all 64 bits. It doesn't clear them. Now, XOR clears the upper 32, or move clears the upper 32. Now push. My assembler doesn't recognize end of line, so it tells by context when the instruction starts and stops. Sometimes you need a semicolon, like define byte or define U8. Anyway, you need a semicolon at the end of that. I'm going to show you my first-person shooter and my flight simulator. They're done all the way from scratch, all the way down to bare metal. I did myself. I don't use a GPU. This is using 6 cores to render. Looks kind of like shit, but anyway, Now here's my first-person shooter. Well, let's go to here's my first-person shooter. This is the source code. It has graphics in my source code. There's the map, and here's some 3D graphics. I wrote my own compiler and graphics library, and look at this. There's a theta. You can use 8-bit characters instead of 7-bit. That was the stupidest thing, whoever thought of 7-bit ASCII instead of 8-bit. Anyway, so here's what it looks like, my first-person shooter. This is one core, not... I could use other cores, but that's a dilemma. What do you do with other cores if you use them? What do you do? Like, I could have 8 times as much stuff. The only problem is, what if they're not available? How do you degrade your rendering or whatever? Anyway, so that's that. Okay, we're going to talk about all the various ways you can boot and how it changes to 32-bit and then 64-bit mode. Because startup happens in real mode, the BIOS starts in real mode. Anyway, this story begins when you make a distribution ISO. So when you make a distribution ISO, you copy the files from TempleOS, from boot, from those directories, and then you say cd file create. Basically, you make a directory with all the files you want in the ISO called distro. Then you tell it everything in the distro directory goes into the image, and then we call cd file create, and this makes a 966 ISO 9660 image file, ISO image file. Now at block, the blocks are 2048. It's pretty safe to assume that. Technically they can be different, but don't worry about that. Anyway, so block 16 is the primary volume, then you have a supplemental volume, then you have a boot record. And anyway, so I think about block 18, something like that, is there's a pre-boot block and then there's a boot block. I think it's maybe it's 19. Anyway, I use no emulation, and when we create this ISO, it fetches the let's see, do we pass it? Anyway, it fetches the boot block that we're going to look at in a second. Anyway, so it puts it in the ISO, and then it puts the files. The file we're interested in is the kernel. The kernel goes in directories 0000 boot, and it's the first file. That's so that on an ISO, the kernel will be at block 20. That's so I can use a third-party ISO creator. So my creator could put it anywhere, but and the boot record would be correct. I could put it anywhere, but I put it in a fixed location so that my boot record would work if I used Magic ISO or something. Anyway, so now we're going to look at when this install boot, this file install boot is included whenever you reboot, and it includes these boot sector files, and it has code to install the boot sector, the various boot sectors. There's a master boot sector, and that when you install that, it reads block 0, patches the code for the sector, and then it writes block 0, and it tells it when you install a master, you tell it the block address of each partition. And when you create a new kernel on a partition, you make the kernel, and then you install the partition bootloader, and this reads the first block of the partition and patches reads the first block of the partition right here, then patches it with the code and then writes it. Or if you're making, when you make a CD-ROM, it creates a boot file. The CD-ROM boot sector is here. This is loaded by the BIOS. No emulation. DL is the BIOS drive number when in real mode when it starts up. So it gets it off sector, what was it, 18, something like that. Anyway, so it always puts it at 7C00, but we don't assume that. So we check to see if it's somewhere else. Then we get the CS and we have the IP we get by doing a call, puts it on the stack, and then popping the stack gets the IP. Then we add the CS shifted over by 4. It has to be on a paragraph boundary. Anyway, it sets the stack. We're going to relocate all this code to just under 80,000, which is 90,000 is the is 9F. 9FFF is the FFFF is the BIOS extended BIOS data area. So under 80,000 is safe, and we put a stack just under 80,000, and then after a block for the stack, then we put we relocate ourselves up there. Right here we relocate ourselves. Then we do a jump up to the new location, and all this code is now at under 80,000. There's a data area here for DAP, which is a structure that you pass to the BIOS when you read a block. Now we're going to be reading that kernel 0000 kernel. So this gets patched when we when we recompile the so we get the we call the BIOS interrupt to get the page for the video. We don't just write to B800. We do it with the put char. Then we check CPU ID to see if this processor is 64-bit capable. If it's not 64-bit capable, we print a message, requires a 64-bit capable, and then we do a jump to ourselves to stop, or to, where do we do that? Not 64-bit, and then a jump to 10. Anyway, if it is 64-bit capable, we go ahead and load it. Now we relocate it up high so we can load the kernel into the 7C. We go through a loop calling interrupt 1342, which is the I like that one. We're only good for 64-bit processors anyway, so they probably have the we don't mess around with the early versions of block read. We use the 64-bit version of block read. Anyway, so you pass it the DAP. We write the buffer address. We keep ES pointing to the buffer we're reading in. We read one block at a time, and we add one block divided by 16 to ES over and over, and we print a progress. Put char is fancy, and when we're done, we my operating system has a boot code. If we boot from CD-ROM or hard disk or soft boot, then we get a different boot code, and so it jumps to the kernel that it loaded in, which is at 7C00. I don't have my assembler. I wrote my own assembler. It doesn't have far jump, so we have to hand code far jump. I have very little 16-bit support because it's you only use a little bit. We're going to cover all the 16-bit code, and you guys have no reason to be using 16-bit code. Okay, so we jump to the kernel. Anyway, so the master boot record goes in block 0. So we covered the CD-ROM. Now we're going to look at the hard disk. If you use my master boot record, it goes in block 0 and it loads. Basically, it does the same exact thing we did with the CD, but it's loading stage 2 of the master boot record. and stage 2 of the master boot record gets patched when you install the master boot record. It gets patched with a table of a block array of the first block of each partition that we want to boot. And it prompts using the BIOS get char to get the this master. Oh, by the way, this second stage goes in the partition file. It doesn't go into there's a gap between 0 and 63, which is used for bootloaders, sectors 0 and 63. I don't use that. I put it in the partition. That's so that you can use an existing bootloader, and it can fall back and do the old bootloader. So when I install, you can fall back and use the old bootloader. So I can install on top of grub and fall back on grub. Anyway, so Windows boots with my bootloader, but not Linux. Linux requires grub. So all stage 2 does is load the first block of the partition and then jump to it in real mode with DL holding the BIOS drive. That's pretty much all you have to do. So when you load when you're loading a TempleOS partition, this is the volume bootloader, which is in the first block of the partition. It got patched with kernel, the kernel.bin block address, and this loads. This goes in a loop using 1342 to load using the DAP structure. This loads in the kernel, and then my kernel is about goes from 7C, I think, up to maybe 40,000. It has to be in the 640, lowest 640. It has to anyway. So my kernel starts in kstart. There's a header on my binary files. This is made by my compiler. My binary files have a 16-byte header. There's a jump past the header, and then there's a type, and then there's a patch table of imports and exports and absolute addresses that have to be patched. In my operating system, all binaries are all code is position independent because it gets patched. And anyway, so I have flat binaries. The code followed by the table of imports, exports, and absolute addresses. This 16-byte header has to be accounted for. So it loads in at 7C. So when I do alignments, sometimes I have to take into account the 16-byte header. Anyway, so first thing it does, it jumps past this. This is some data we're in real mode, 16-bit mode right now, and my assembler doesn't support segmentation, basically 16-bit code. So what all these offsets are 0 based. In my the assembler codes this at 0 pretty much, not quite 0. Anyway, this offset has a value of 0. So what we do is we set the data segment to 7C, and now for the 16-bit code, this offset will be right. We have to get to that point. So here's the global descriptor table. Has some hard-coded values that are fixed, and it calculates the boot data segment and the boot code segment because I made it independent, so it doesn't have to be loaded at 7C 00. These are for 32-bit mode. When it's running in 32 before it switches to 64, we use this data segment and code segment. We have code segments for 64-bit. We sometimes we switch back to 32-bit, but we never switch back to 16-bit. We have 64-bit code segment. We have a ring 3 in case you want to mess with ring 3. Everything's ring 0, but there's a demo in case you want to mess with ring 3. And there's the task registers. I have all that stuff fixed. Anyway, it has memory. It has space for the BIOS information we're going to collect, and then it has the Atom task record. So we're starting up here. We do the same trick, pushing the IP, getting the IP, calculating the new address. Except this time we don't shift it. We shift it the other way, or do we? I don't know. Anyway, then we return far. Okay, that just sets the code segment so that we don't have ambiguity if we used a different bootloader. Anyway, then we this decrement is because of that 1 byte paragraph I told you about at the beginning. Anyway, so we calculate a checksum, see if the kernel has a correct checksum. We write to ES is B800, which is not the BIOS. We just plot or write to screen memory. Okay, or XM, what's a checksum error? Oh, okay, or checksum error. Anyway, so when it continues startup, it sets, we're in 16-bit run level. This is streaming code, so this code gets this gets executed at compile time after it's been configured, and it inserts a line of code into the stream of code. So during compile, you enter a config for what video mode, and then it makes code for that. See, the config time is compile time, and so this exe does compile time. Anyway, then it calls interrupt 10, and it falls back on text mode if interrupt 10 doesn't work. So we change to 640 by 480, unless you say text mode. Mouse, this mouse enable doesn't help. So either you have mouse or you don't have mouse, and this mouse enable doesn't help. Anyway, so I commented that out. I get the memory maps from E820. We save those, and we call an interrupt to find out how many PCI buses we have, so we don't have to check 255. I think typically you have like 6 or something. We set to E820. We initialize all regs to known values. Then we now, is this a are we in we're still in 16-bit mode, aren't we? Yeah, we're doing BIOS calls. Anyway, now we let's see, we set up those boot sector or boot data segment, code segment that we had a few bits of information missing. Then we set up a pointer to the global descriptor table and set the size of global descriptor. Then we do load global descriptor. Then we change the protected mode. Now we're in 32-bit mode. Actually, we aren't. I forget. I think it happens when we jump to this code data segment, which is this next. We skip this little bit of data. We have more room for data now that we're not limited to 64K. So we have some more data. Those are basically operating system global variables. So we enter point. Now, if we're doing a soft boot, which means you're rebooting without actually doing a hardware reboot, then we jump in here in 32-bit mode. So we load the flags. We change the run level number from 16 to 32-bit. And that doesn't quite look right. Oh, because we're doing a soft boot, we want to clear out all the other run level bits. So we only keep 16, and then it doesn't turn it off. Anyway, so in case we came through on a reboot, all these variables would be uninitialized, because they'd be left with garbage. Anyway, so we go ahead and now we're preparing for 64-bit. What do we do here? We're patching absolute addresses. Before we can do the 64-bit C code, we have to patch all the absolute addresses. There's a list of absolute addresses that have to be patched. Anyway, let's see, what do we do here? We patched. Then we find the PCI 32. There's a thing called a PCI BIOS for getting config information that runs in 32-bit mode. Anyway, we never switch back to 16, but sometimes we switch back to 32 to do that PCI BIOS. So we initialize memory, and then we initialize 64-bit mode. Let's go look at the memory. The memory gets identity mapped. I think I picked 128 gig. Just everybody gets 128 gig mapped, but it's not all present. It's mapped with 2 meg pages, so it's only, I think, maybe 200K or something page tables. Anyway, it's 2 meg pages. The first 2 meg is 4K pages, so that we can do video memory as a write through. And so we map 128 gig or something, except for E to F. This is for device memory. We map this as uncached. Now block 0 or page 0 we set to not present if you do a compiler or a config option. So I can get a page fault on dereferencing null. That's only if you set that config option when you recompile the kernel. So this sets up the block pools, and then when it's done, we come back to kernel start down by let's see, we init the memory. 64-bit mode only works with paging. You can't run without paging. So we call init emt64 em64t. So to do that, I don't know what this is. We load CR3, which is the virtual memory, or paging. Maybe that's paging. This changes to 64-bit mode. This EFR thing, write model specific register. This, what is this? We enable paging. So we set our pages up for 64-bit. Now we set the GDT with, I'm going to look at that in a second. Okay, so then we jump to part 3, CS. Now when we do a soft boot, we have to change back to 32-bit, and then either we halt or something. I forgot what we do. Anyway, we were going to look at the GDT. The GDT is set up for 64-bit. These are 16-byte entries. That's because 64-bit is 16-byte. And the upper, basically, this will work as both a 32-bit and 64-bit GDT, because it's like there's a gap. When you're in 32-bit mode, it's like it's every other one. When you're in 64-bit mode, they're all used. Anyway, so we call, what else do we do after we call enable? So we're cruising through here, and now we're in 64-bit mode. By the time it returns, we set the run level to 64-bit. Floating point init, save the state so we can, I think we use that for initializing tasks to an initialized state. And whenever we initialize a task floating point structure, we copy that initialized one. Anyway, we initialize the CPU. GS is the CPU structure, which is the core, and FS FS is the task, which the task structure. All this sets up Adam's heap. Adam is the father of all tasks, like Adam and Eve. This sets up his heap and his task. He has to be set up specially. This gives him a. We haven't quite done a full-blown init with the E820. When we add all those items, we do that later. We give them an initial heap. So then we jump to kernel. Anyway, where were we? I was going to say one more thing. Okay, so it initializes the Adam task, sets up the task queue. Adam is the father of all tasks. Then when you do multi-core, you have to you do a sippy, something like that, and then it jumps to a vector. I forgot where I put this. Let's see what the vector address is. Let's see. 7F. That's interesting. I think it's 7F000 or something like that. Anyway, when it starts up, those get vectored. This code gets copied from start to end, gets copied down to that vector address, or up to that vector address. What this is invalidate cache, right back invalidate cache. What do we got here? Oh, we load the GDT. It's the same GDT. Everybody uses the same address map and everything. We set to 32-bit mode, and we jump we jump up. Now we're out of that chunk that got loaded. Now what it does is it puts a lock on the count of tasks, and then it assigns itself a core number. Puts a lock on the core. Then it assigns itself a core number, and if it's too big, it halts. We can only have so many. That's just being professional. So it initializes. It goes to 64-bit mode. Initializes floating point. Sets GS to the new core number. It figured it out from the count. We have an array of core of CPU structures. Sets the GS to the CPU structure, and Seth is the name of Adam's sons in the Bible, and Seth is Adam's first son or something. Anyway, so each core has a Seth task, which is special. It goes in a loop like a server, and you give it jobs. It can either spawn a task or run a job. So that's what these do. They halt until they get interrupted. And then they do something. Now, one more thing. Back in the start, towards the bottom, it jumped to. So all this is assembly code. Then we jump to kernel, and where that is this is the end of the module, kernel, and now we're in C. From now on, almost everything is C. So we mark not present. That's that's the memory in the E820 map that's not present. We mark not present. We go ahead and initialize all the global variables. We have various run levels for when we have raw output available. When you can write to the screen. Remember, it's 640 by 480, though it looks like text mode. It's not. It's graphics mode. We enable interrupts, unless it'll run in text mode as a fallback. Here's where we turn on interrupts. We loaded the interrupt table, calibrate, timer, initialize mouse. Then we start initializing our block devices, which is our CD and hard disks and RAM disks. Then we load the compiler. This is where it crashes a lot of times. If somebody were silly enough to try and boot from a USB, it would crash when it tries to load the compiler, because this is done with direct hardware access, not BIOS. And basically, if you don't have direct hardware access. If you can't load anything and you can't do anything from a USB memory stick. Don't even try. And you can't compile outside because the bootloaders get installed and patched with the kernel block number. So basically, there's a lot of people who are stubborn and try to run without my compiler. They try to install without my installer, and they try to boot from a USB, and that's just not going to work. Anyway, when it's done, it executes Atom1, which is like the autoexec.bat. This compiler starts chugging away on this code, putting it in Atom's symbol table. Then it goes to Atom. So this is the headers for all the kernel and compiler. These are the headers. And then it goes to, there's 50,000 lines compiled ahead of time. And then in this Atom directory is another 50,000 that's compiled just in time. So this is Atom 2 is all this stuff that gets compiled just in time. And then finally at the bottom it goes to the, after it logs in, it goes to the home directory and does Atom 3. So in your home directory, if it doesn't find a file, it searches the parents. So trivial solutions, these are all the, this is the home directory Atom 3. So all these get loaded into Atom symbol table. And that's how booting happens. Okay, we're going to cover some of the graphic editing features. This is a 16 color bitmap that I got from Windows. When you're working with Windows, don't let Windows modify your primary partition, because my FAT32 support doesn't support all aspects of short names and recycle bin and stuff. So use a different partition from your primary partition for transferring files from Windows. In order to transfer files, you need VMware Professional or WinImage. Anyway, once you get one in, then enter and then type it. Okay, now we just put a BMP file on the command line. Now I'm going to put it on the clipboard, if I can find it. Control T, toggle, there it is. Now I put it on the clipboard, come into here and paste it. First I'm going to make it transparent. So Control T, Control R to edit. Now there's three main menus: the edit menu, the vector menu, and the bitmap menu. Okay, I'm going to set the color to transparent and then flood fill. So okay, so, and now it's transparent. If I move, you can see my cursor sticking out through there. So Control T, Control R. Okay, I want to show you this sidebar here. Is the vector commands are in order. If we, I'm going to set snap. So if I draw a rectangle, it's in order. Now the neat thing is I can come up, cut and paste, and now it's now the rectangle is drawn before the cat. So let's go ahead and let's do another. So let's do a yellow rectangle. Okay, now let's shift points. We go to the edit menu, shift points. Oops, that's not what I wanted. Oh, I'm messing this up. I wanted to move the cat centered. Okay. Okay, now I want to merge these. If you put it on end and you go to the vector menu and then you go to create edit bitmap, this will merge if this is on end, you're in use extents. I merged them into one bitmap. Now I want to show you something else. You can work with layers. If you do multiple, don't do everything all in one. You can use the clipboard. This is really powerful. So you can create stuff separately and then paste it together, edit, insert clipboard, insert. I'm making it 3 times now. Shift points. So let's make one of these transparent. So let's go to the vector menu. Now let's edit one of these bitmaps. And let's transparent. Okay, oh, this is a problem. It's doing the whole, not just this bitmap. Oh well. We're going to set it to transparent and flood fill. So I'm suspicious. Okay, now we can vector edit shift points. So we turned that one into transparent. So you can work with layers if you know what you're doing. Anyway, now I want to show you a couple tricks. You can Control-Alt-Z to zoom. Control-Alt-Shift-Z, zoom out. Control-Alt-G makes a grid. Control-Alt-Shift-G gets rid of the grid. Now the other trick is let's get out of this. Let's create a bitmap that's bigger than the screen. We're going to go from 0 to 1023. 0. Let's go 255. Okay, now I think the whole thing's green. Okay, the whole thing's green. Anyway, if I do Control left drag, I can access an area larger than the screen. Control left drag. Okay, so I can even, this is kind of hard to do, but I can even draw a rectangle larger than the screen. Okay, so I have the button, I'm holding the button. Now I press Control, then I drag, and with the, I'm still holding Control. Now I press the button because I have to continue the rectangle. Release Control. Let's see, transforms. You can do 3D editing, but that's not very easy and it's tedious. This is TempleOS. I'm going to cover 10 ways to do Hello World. So the command line feeds into a C compiler. So the first way is to type in a program at the command line. Now, any statement outside of a function executes immediately. So if I say main1, we got hello world. Okay. So this is sitting in memory. We can unassemble the function. It's compiled, it's not interpreted, and there it is. It calls print, and there's the string following the function. Okay, so the second way, we don't need to say print, we can just say a string by itself, because in Holy C, a string by itself is printf. So now we say pound include hello o2 cpp.z. Now we have to hit a semicolon because it analyzes the token ahead, and anyway, that's a special quirk of the command line. So let's just for the fun of it, I'm showing you the ed command. Normally you okay, anyway, so we don't need a main. We can just print a string by itself like this. So if I do a directory, do number 3, so 4, now we're doing a function with a parameter, sending it to print. Or we can do a string by itself, %s, remember it's a printf. Then we're calling it, sending it a string. Now if you don't use a comma, then it treats it as the the format string. That's a slight variation. I'm just showing all the variations. So now we got 3. And this is assembly. We have a string with these don't have zeros at the end normally, so we have to add the 0, or we can include the 0 this way. Now we're making a global symbol with the colon. A single colon is not a global symbol. We're calling put string. We have to save the RSI segment register, or not segment register, the RSI register. Then we're calling it. Now I'm going to hit F5 just for, well, no, let's do it the other way. If you hit F5, it executes it immediately. Anyway, that's the editor, similar to Visual Studio. So if you don't use an ampersand is the same thing as an import. We use an underscore just as a convention. It's not required for C callable functions. That's a C callable function. I put an underscore on it. So we have an enter. This is an assembly. You probably have never heard of this assembly, x86 assembly command, enter and leave. This just sets up the stack frame, push BP, move BP, SP. Anyway, so we save the register. Now we're calling it. We get the first argument. Now we're binding underscore main to a C symbol, and then we're calling the C symbol. So now we hit, just for fun, let's get a list of local symbols. So at this point, these are like environment variables, scope. It's the scope of environment variables. So at this point, we have this many symbols in our symbol table, and we can browse them. We can unassemble the functions and stuff. Anyway, so number 7, this is a ahead of time compile. We're telling it to include all the symbols in Adam's symbol table. Adam is the father of all tasks. He's like Adam and Eve. Anyway, so we're going to ahead of time compile this. Now we have a number 7 bin. We load it. Number 8. Instead of using the pound include, we're doing an import instead of the pound include Adam ahead of time. Okay, so now we ahead of time compile. Now we have to load the bin. Now we made a we have to make a I accidentally deleted that file. We have to make an extern. Okay, so there's a header file for this binary that creates C symbols. So we include it. So now we have a main 8. which is a valid. Okay, now number 9, we're going to, you know what we're going to do? We're going to include it into Adam's symbol table. Adam is the father of all tasks, so this makes it system-wide. This is like a DLL, you could say. Anyway, so we include Adam include. Now I'm going to go over to this other task, in main 9. Now it's a system-wide symbol. I'm going to come back here, and number 10. Okay, we're doing a ... function that creates, you know, like this in C++. Well, when you have a ... there's an argc and an argv automatically declared, just like this in C++. So I'm going to go ahead and, so we're going to print the 2 strings as 2 arguments. I'm going to hit F5. There, it got hello world. Okay, so that's 10 different ways to do hello world.
Okay, we're going to look at some unusual features and lose those. We'll go to the kernel source code directory, and there happens to be a file on interrupts, and this has a feature I want to show you. You see this blue entry? That's a macro, and what that does is it does whatever text you want. It sends to a new spawned shell in a pop-up window, and it executes that text. So in this case, it does a grep, and then it does a view. We just looked at it by hitting Control T. Control T toggles plain text in regular mode. Now, if we click on it, it does a grep. And in this case, we wanted to direct the attention of whoever's reading the source code to look where this entry is executed, just as a convenience. Now you see it's blue because it's a macro, and the red ones are links. Just in this case, it's to a symbol. Anyway, that's consistent with the command line. These red ones are links to files, and these blue ones are macros, which change directory and then do a directory. So for directories, it will list a directory, and you can see it's consistent with the with your main menu, your main personal menu. Has blue and red as well. And now we'll go look at some other features of the lose those text files. They have superscripts and subscripts, and blinking and underline inverted, and widgets like a button. Now if we run this, you can see it sent it to the command line. See, this is the command line. Anyway, so you can also put superscripts and subscripts in labels, and the compiler understands them. So if you want to do that, you can do that. I don't advise it. It just doesn't seem like a good idea. But if you want to do extended characters, that's for ASCII or for codes 128 to 255. You can put extended characters in labels, and the compiler will understand them. So we just did a little smiley face. Anyway, so you can also put graphics in source code, and you can send it to the command line. So like in this case, this program runs and it sends some graphics to the command line. So those are just some unusual features. Okay, now we're gonna put some graphics on the command line. These are vector graphics. We'll put a color red, width 5. I'm gonna make a smiley face. You can it's kind of like doing graffiti on the command line. Now, the sidebar with the vector commands can be edited with the clipboard. So, for example, we can we can position and put another width in here. And then let's look at it. Okay, now the bottom one is wider. Now if we can come and move them on the clipboard so that only one is wide. See, kind of a fat lip or something. Anyway, now we're going to take this from off the command line, cut, and put it into a file. Now it's we have to reposition it. We'll set the origin, and let's see. Anyway, now let's take a look at the format that this is stored in real quick. Edit as text. Here's the color, the width, circle, line, 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 width. This is the raw data. You can modify this by hand if you want. We'll make the width 5 or 10. Now it's all wide. Anyway, the reason I did that, we want to look at the this file is stored uncompressed because it ends in a CPP and not a CPZ. So if we do a directory to convert it and change the last letter from Z to P or vice versa, now let's look at the you can access disk blocks yourself directly with we just did a full directory which shows the cluster numbers, and we're gonna display a cluster. Here's the ASCII data, and then here's the raw text, the raw binary for the vector graphics. Anyway, now if you use another parameter on this dump cluster, you can edit it and then write it. So everything is accessible on the disk. You can access any block you want. Now you can also access any memory you want. And one interesting thing is the task record for the current task. FS holds, that's the FS segment register. It holds the current address of the current task record. You can see the task record is also shown up here on the when you're at the command line. So we're going to dump. There's a command that lets you display a record, and it accesses the compiler's task structure. It accesses the compiler's information and lets you edit it. We can change the left window coordinate and change it to 5, 1. Anyway, the command line has a dynamic LTFD. Is a dynamic dump that shows data live in memory. We can modify it, or anyway. Okay, we're gonna go try the Moses game after Egypt. Okay, so there's camp. If we break camp, the number of people gets randomly bigger or smaller. Anyway, oh, watch this. They'll do golden calf. They all run in a circle, and that's from the Bible story. Few clouds. God was a cloud. I was gonna have it lead them around or something, or make
figures in the clouds. Anyway, let's see. Hold court. A woman commits adultery to a child. Ooh. Punish. Hold court. A child commits adultery to a child. Really punish. Hold court. A child commits idolatry. Really punish. Okay, so view map. They wandered 40 years in the desert. So this must be what they did. Okay. Make water. He struck a stone and it made water. Anyway, let's see. When he held his hands in the air, they did well and they did good in battle. When his hands got tired, they started losing. Moses begged for meat. They got sick of the manna, and they wanted meat, and God gave them meat, and they got sick and died. Anyway, so here's the cool thing. This really works. If you talk to God, He'll talk to you. So let's ask him. I guess they got seagulls from. Let's see. What can we? If you do an offering, he'll talk. How about? Did you make any babies today? Okay. 20% of the net profits you derive calculated. This is from the Bible, small print. God wants 20%. Anyway, God wants 20%. Let's go to, I do Moses comics. Why don't you make the sun stand still to show them? Oh, come on, would you settle for a wet blanket? That's a reference to this one story where dew formed on this one blanket. Anyway, yeah, go talk to God. Let's see. Let's ask him, let's see. What's he getting for Christmas? How about that? God says. What's he getting Jesus for Christmas? How about that? The way this works is it's just a stopwatch for random numbers. Okay. Well, anyway, how about that?